Morning, one and all. Today, we will be exploring how to identify flowers using the VGG19 neural network. So before we move ahead, I will just give you a quick gist of how the data looks like. So here we have the dataset. It is pulled out from a famous Kaggle competition. Here we will be solving the challenge using a VGG19 neural network architecture. So these are the flowers that we have here. We have in total 18,540 flower images for the training, and this is for the testing, and which we have 1,237 images. So we have a valid supporting Excel sheet which tells which class the corresponding image belongs to. So the images are identified by the respective image IDs, and here we have the category of the respective class of each flower. In total, we have 102 different classes that must be classified. So moving on, I will just quickly illustrate how a BGG19 architecture looks like. This is how it typically looks like. So we have the convolutional layer, the max pool, and the max pool with multiple convolution layers embedded in between. So VGG19 is a typical convolutional neural network architecture. Right. So before we now that we have done with the basics, let us go ahead and start executing this on a Jupyter notebook. So let's follow the old traditional method which we always followed: importing warnings, CV2 for OpenCV operations, NumPy for NumPy arrays, pandas for pandas operation, and data frame operation. TensorFlow is used to, since we generally use TensorFlow 1.14 version in our deep learning tasks. And here comes the Keras family. So we have Keras applications, Keras optimizers for optimizing a model, and then we have the sequential model, and we have the various layers of input layer, dense layer, batch normalization, max pooling for the convolutional neural network we're going to use, dropout for reducing the chances of overfitting, and flatten layers. Okay, and we'll be using the image data generator. So this is a very interesting functionality provided by Keras. So what does the image data generator do? So image data generator does nothing but bumps up the number of images in different orientations, which we shall see later. All right. So now that we are done with this, let's execute this cell. Yes. Now we have the two data sets. You have the training data set and the testing data set. So again, these data frames point out to the image ID, which is nothing but the image name, and the class to which the image belongs to. So the feature extraction part we are going to do directly from the image by the neural networks. So as we had discussed in our earlier sessions previously, feature generation is automatic and automated in a deep neural network for images. Yes, so now that the image and data frames are loaded, we will append the data frames with .jpg for the image ID attribute. So why do we do that? And again, reiterating back, so these are the image IDs, which are nothing but image names. So accessing them, it will be a challenge because the images are not properly aligned to their image names. Hence, we are going to append .jpg to the image names through pandas. Let's see. Yes, getting back, we'll do this and the cell. And since we are short on time and training for 102 images will time is pretty significant and would require a higher level of GPU configuration. So if you have a strong GPU in your end and a lot of time at hand, I would suggest you to go and take classification for all the 102 images. But here we will pick 3 categories of images and go ahead with their training. Okay, so first 900 images for training, and the testing is for 900 to the remaining number of images. We'll run this and we're done with it. All right. Now that we have the data for the 3 classes, right, we are going to apply the image data generator that I had previously mentioned. So what it does is, these are the different operations that an image data generator can perform. So it is going to rescale the images, go into and out, 255 times. Rotate the image by an angle of 40 along all the axes. Shift the width by 0.2 and again not by 0.2. Repeat the same for height. Okay. Similarly, we have the shear range. the zoom range, the horizontal flip, which is the mirror image on the horizontal y-axis, and the vertical flip along the x-axis, and so on. This is how we're going to generate multiple representations of the single image. All right. So you might have a question, why are we doing this? We are doing this because, firstly, we are dealing with deep neural networks, which have a tendency to overfit all the time. Since this is a challenge, we are going to generate multiple copies of the same image to help the neural network understand the modeling process through a wide range of data, different samples of data, to model the scenario better and hence avoid overfitting. All right. Here we are going to obtain the images from the training dataset directory and dataset, and create a trained data generator, which we will be using for training our Keras deep learning model. We will run this. We have found 900 validated file names belonging to 3 classes. Okay. Similarly replicated for the testing dataset. 69 images we have of testing. Now that we have done this, let us load our VGG model. So we have Keras applications, VGG19, we have ImageNet weights, and go ahead with it. Right. So now that we have loaded the image, we have mentioned the input shape as 224, 224, 3. So you might be wondering, what does this number denote? So I'll just quickly show you what it means. Okay, this is the image, and let's see its properties. So we have details. Yes, it's a color image on X and Y axis, 224, 224, 3. All right, and on top of it, we are going to load the images as by rescaling it to the size 224, 224. All right. So why do we do this? We do this so as to maintain a uniformity across our data, since we are dealing with a deep neural network which accepts images of a specified size, in which we are specifying the size of the images 224 by 224. All right. Now what we're going to do is we're going to freeze a few layers. All right. So we're going to freeze all the last 5 layers by mentioning the trainability factor as false. And similarly, all the layers from 1 to 4, we will make it as true. Okay. Now that we have closed this piece, we will go ahead and mention the input shape as 224 by 224 and name this layer as image input. All right. And the output is going to be attached to the input. Okay. Now that we have done this, we will apply batch normalization, max pooling, and a bit of dropout. And since we are dealing with the convolutional neural network, we will be applying pooling layers across it. And you might be knowing why we're using dropout, because we want to avoid the scenario of overfitting. So we're going to set 20% of the nodes in along this particular layer to 0 weight, which basically means these nodes are not going to participate in the training process. Similarly, let us extend it across our neural network, which we are going to build. And finally, this is going to be our final model. Okay, this is a combination of the VGG19 neural network with a few frozen layers and a few custom layers input by us. So it looks pretty impressive. I feel this is good to go ahead. Now that we've done this, let us compile this model. So we'll be using the categorical cross entropy loss function. Why are we using the categorical cross entropy loss function? Is because we are just a classification problem. All right. The optimizer will be IDA delta. I would highly encourage you to experiment with different optimizers. And since it's a first iteration, let's go ahead and set the metric as accuracy. But ideally, I would prefer as a data scientist the metric to be the validation loss. Okay, let's go ahead. We'll define the step size, the number of images in training data by the batch size for the training data for training, and similarly for the testing. Okay. Now that we are done with this, we will define the generator as train generator, which is something by the training data, the number of steps per epoch, the number of epochs is 2, and the verbosity as 1. Since it is the first run. Okay, just go ahead and get done. All right. So first at epoch, we have they run as follows. We have loss is 0.9 and accuracy as 0.62. There is 62% accuracy. Not bad for 3 images. Okay, in the second epoch, we are going to capture, and I notice that the loss is 0.35, which is a significant drop from 0.96, and the accuracy has shot up to 85%. Quite impressive for a three-class classification problem in just the second epoch. So I would encourage you folks to bump up this epoch to at least 10, plug in a few callbacks as we are discussing in our other videos, and try to receive a better model out. I'll just run this thing and let's run the predictions. So since it's Keras, Kaggle competition, we do not have any tracing data to compare it against. Though we have obtained this split across a training data set to get a good estimate of the accuracy, we'll just prepare a submission file now. Okay, we predict the data set. We had a test data set, number of steps, and verbosities. Right? Okay, we'll mention the predicted class indices as follows. It's nothing but the maximum argument and among the predicted axes. All right, we have the labels, class indices, and we mentioned the labels in a list. And now we are going to prepare the submission file as you always do for your Kaggle competitions and save it into results.csv file. And we are good to go. I'll just quickly show you the results of CSV file. It is generated here. Here we have it. This is how it's going to look. So for our selected set of images, we have the image ID and the category. That means the class to which this image belongs to. So this is our applications of VGG19 to solve a three-class classification problem in recognizing the right flower. If you have folks have any doubts, you can refer to my GitHub where this notebook will be put up there. And if you still have any challenge in executing this notebook, please reach out to me in the comment section. Thank you.